Hello world, it's Siraj, and it is a beautiful day to do some machine learning. Thank you for being here. I love you. What we're going to do today is we're going to talk about explainable machine learning, and I thought about a lot of different angles to be tackling this topic from, but I ended up deciding on just picking one, and that angle is one single technique called the Grad-CAM method, and it's for computer vision. Grad-CAM stands for Gradient Class Activation Mapping. A lot of words, a lot of jargon. You'll know it all by the end of this video. I promise you that. And so what you see here is a demo of this. You see this picture of a dog and a cat, and what happens is after the Grad-CAM method, well, first of all, a convolutional network will classify that image and say, here's a dog or here's a cat. And then the Grad-CAM method will say, here's why the convolutional network predicted that this was a dog or say this was a cat. And we want to figure out how the Grad-CAM method works. That's the point of this video. I want to explain to you how the Grad-CAM method works, both using mathematics and using code. I found a great example of this on GitHub by fairyonice. And fairyonice has so many great, she's got so many great examples for so many different types of networks, but there was one in particular that I liked, and that was her Grad-CAM example that I uploaded to Colab, kind of, shortened it, cut out a lot of stuff, and then made sure that it was video friendly. So that's the demo for this video. We're gonna go through that code at the end of this video, but there's a lot to talk about when it comes to explainable machine learning. Because, I've been watching so many videos on this topic of explainable machine learning on YouTube. There are a lot out there. Just search explainable machine learning, you'll find a lot. But there's not a lot of views for any of these videos, which is kind of sad. And also, something I've noticed from these videos is that there is so much of I don't want to say bias, but an opinion. This is such an opinionated field because, a lot of researchers who spend, entire careers are built on top of defining the semantics of what all these terms mean. Is it interpretable? Is it explainable? What constitutes explainability / interpretability? When should a model be interpretable? What methods are valid, etc. There's a lot of different, opinions on what explainable really means in machine learning. So rather than go into this diatribe about what explainable machine learning is, I'm going to define it, I'm going to overshadow these researchers and say, this is what it is. I'm going to try to give you a very brief, high-level overview of what explainable machine learning is from many different perspectives, and then we're going to talk about the Grad-CAM method together, okay? So the standard example here for machine learning is we got some data, we feed it to a model, and then it gives this prediction, and it's got an error. Explainable machine learning is all about looking at that data and saying, why does this data conclude this prediction? Or not just the data, but the model. Why does this model conclude with this prediction? And so there's a lot of dimensions of interpretability. We can define interpretability as equivalent to explainability or not. There's a lot of opinions on what that should be, but let me just say this. There are three really big dimensions of interpretability, and that start with the data. So the data is which dimensions of the data are most relevant to my task. So let's talk about heart disease prediction using medical imaging. Let's say we've got some images of heart disease. Coronary calcification is the medical term for this. And our model will then predict whether or not a given heart disease image has coronary calcification or not. And when it comes to the data, let's say we build this model, it's robust, it works, we give it to a hospital, it's put into production, and then it makes its first prediction, and then a radiologist is like, well, wait a second, why? Why is this image a heart disease picture and not, and as opposed to not being one? Because I don't think it should be with my domain knowledge. There are three angles we could tackle that from. The first is from the data angle. What are the biomarkers? What are the initial features from the image that give rise to that prediction? Is it, what is the spatial location? What is the color density? Those are the features of the data. So that's one dimension. The other is the prediction itself. It's not just about the biomarkers, but the weights as to how much each is relevant and what are the connections and relationships between them that give rise to that prediction. Not just the data itself, but the relationships between them. And then the model itself, like those patterns. Why do those patterns belonging to a certain category, what do they typically look like according to a model? So we could say, typically, one pattern is if a patient is above a certain age and they have, a certain set of features, lifestyle attributes, then they will likely have heart disease. So those are the dimensions of interpretability. And when it comes to these Kaggle competitions, for example, a lot of times explainability is important, and that's why, despite neural networks working really well, a lot of these competitors don't use neural networks because they're not as explainable. And so there's this trade-off, right? We can either say, let me just train an interpretable model, like let's say a decision tree, a decision tree with if-then rules, or random forests, which are collections of decision trees, or some model like that. Or let's train the best model, it's deep neural networks, and not have that built-in interpretability and then try to interpret it later. So there's a trade-off between accuracy and interpretability, but it need not be that way. We can have both. We can have both accuracy and interpretability together. So before we go into the math, let me just show you some really cool tools that I found that I want to talk about, that I really liked, and I want to share with you. The first one is this interpretable machine learning book that I've never seen before by Christoph Molnar. Great work, Christoph. This book is free. I mean, you can pay for it, but it's also free on the web, which is amazing. Literally, the entire book is about interpretable, explainable machine learning. So many different techniques in here with images, adversarial examples, counterfactual explanations. I mean, there is a lot of theory that goes into this, and this is the book that you should read if you really want to learn about this. So check out that book. And then there's this amazing, huge list of GitHub. Basically on GitHub, there's this like tradition where like someone will make a repository and they'll put the word awesome before something, like awesome synthetic biology, awesome, whatever. In this case, it's awesome machine learning interpretability. And this is basically the mother lode of everything. Every book, even the book I just talked about is in here. All other interpretability and fairness resources and lists. You got YouTube playlists. You got, like I said, this is a huge field, and it's one of those fields that it intersects with human values and it intersects with culture. What is considered explainable in your culture as well. That's why I think AI safety and explainability is just not that talked about, because it goes into your deep human belief systems, right? What constitutes explainability? What is worthy? What is considered a worthy explanation? And there's a little bit of a gray area there. So that's why it's interesting, but there's not as much interest. But hopefully we can change that. We should change that together. I talked about explainable AI before in my AI in 2020 video. Again, great looking repository. Again, these repositories that I'm showing you, they're not like TensorFlow, but with explainability or something. They're not just like deep neural network libraries. They've got decision trees, they've got support vector machines, they've got the models that are more explainable. This one is really interesting. I think it's by Microsoft of all, it's by Microsoft, which is amazing. And it's been kept more up to date than that XAI example that I just showed you. Good job, Microsoft. You're killing it over here. They've got a lot of pre-modeling explainability, that is like exploratory data analysis. And they've got a lot of backends, scikit-learn, Plotly. Good. So that's another one. And then one more, and that's IBM. IBM's got this really cool repository called AI X360. And the great thing about this one is that they've got a lot of Jupyter notebooks that are built for a lot of these techniques, like SHAP, which is one of them, and it goes into a lot of detail. So good job, IBM, on doing that. So definitely check those out. And then I'm just going to give a shout out to Papers with Code, because this is like the way to learn machine learning in 2020. Like, this is me saying this. The guy who's built a brand around learn machine learning for beginners. This is the way. You go to paperswithcode.com. You type in whatever you want to learn about. Let's say it's explainability in this case. Look at my wonderful spelling. Explainability. Possibilities. Okay, explainability. And you're going to get so many great papers. You're going to get code. You're going to get videos. Look at this beautiful stuff. And what you do is you just open up both in a tab, right? You click on one, and then you say, here's the paper, open. Here's the code, open. And go into both. I'm looking at the paper over here. I'm looking at all these different code examples. Look how beautifully indexed this is as well. You got to admire the work that went into this. It's not just one implementation, it's 27 implementations, which is amazing. Okay, so there's that. Now I want to go into the math of the Grad-CAM method. All right, ready? Here we go. All right, so convnets. Convnets are awesome. Here is how they work. We've got our input image right here, image, and this image is full of pixels. Okay, so let's just call one of those pixels pixel ij. So that's the location, right? The x and the y coordinate of that pixel. You might be thinking, why do I care about ij? Don't worry about that yet. We have an image, and it has got one pixel called ij. Now, what we're going to do is we're going to feed this image to a convolutional neural network. Okay, so we'll say this is our convolutional neural network, or CNN, for fake news. Oh no, that's something else. Sorry, convolutional neural network. Why am I doing this? Why am I writing this as opposed to just showing you static images? Because it's fun. This is part of the fun of teaching, right? So I just want to do this. So here we go. So we've got a convolutional neural network, and it's got they're called blocks. I call them blocks, convolutional blocks. Convolutional blocks are basically a series of operations. You've got a convolution operation, and then you've got a pooling operation, and then you have an activation, and you just repeat over and over and over again. Actually, sometimes there's not even an activation, but in general, we have our convolutional block, so we'll say CONV. We have our pooling block, our pooling operation, and then we just repeat over and over and over again. So we'll do it again. Conv, pooling, conv, pooling, conv, pooling. So let's just say 2 layers of that for us in this case. So convolution pooling, and then we have our final layer, which is our classification layer. So we'll say fully connected, our fully connected layer. So we can think of a convolutional network as having 2 components. The first component, this part right here, the main part, is all about feature extraction. Sorry. And then we have our next part, which is all about classification, what is in this image. And that's what the fully connected layer is for. So what we want to do is we want to say, given this image, it's going to go through all of this, and then it's going to say, here's the output. And the output is, let's say, 96% dog. And let's put a little doggy image there. This is my dog. Don't hate. Okay, so that's the operation right there. So what we want to do is figure out why it picked dog. And so the great thing about convolutional networks, little primer on how they work, by the way, you'll need to know this. So we can think of an image actually as a matrix of values. With 1, 0, 0, 1, 0, all these numbers, right? So that's the input. That's the input matrix. And then we've got what's called a filter or kernel as well. A filter is at each layer. We've actually got a lot of filters. And what the filter will do is you can think of the filter like a flashlight. 1, 0, 0, 0. And so what happens is the filter is going to be applied to every part of that network. And by applied, I mean a matrix multiplication. And the result of that filter being applied to all of those parts of that initial input is going to be a feature map. Feature map. Okay, and so that's the result. And so each of these convolutional blocks has multiple filters, and thus multiple feature maps are created. So for VGG16, there's like more than 512 feature maps. There's like a lot of feature maps there. And the reason that I even showed you this process of what it's doing, input times the filter, gives you the feature map, and then you apply pooling, and pooling is basically a way of reducing the dimensionality of the input. There's a lot of techniques, but let's just say it's a compression technique. And so we've done that, and now we've got our feature maps. Okay, so the reason I'm showing you all of this is because for GradCAM, GradCAM uses the feature map to create that heat map at the very end, because the last feature map contains the features, contains the spatial and critical information about that predicted class that we can use to create a heat map out of. That's where that crucial information is. It's in the very last feature map. And so what we want to do is we want to see, how does every single pixel in that initial input image contribute to that feature map? And so that's where the beauty of this technique and the math comes in. Okay, so here's how convolutional networks work and what it's doing, and now let's go into the math behind GradCAM. Okay, so step one is to compute the gradient of our class, like our predicted class, let's say it's dog, of our class with respect to a of k, or ak. It's a good day I didn't have to use my ak today, just kidding. Here's what it is. We have our final feature map. We're going to call it A. Okay? And there are k feature maps. So A of k is a subset of all real numbers u, x, and v. And so this represents our final feature map, which is like that last series of numbers that's been computed throughout that convolutional neural network. This is our kth feature map, and this is how it's represented mathematically. What we want to do is we want to see how all of those initial images, ij, here's where that ij comes into play. ij, how they play into that final feature map, because we want to see what parts of that image, because this is the most crucial element in creating a class prediction for our convolutional network. It's got everything that we need in here. But we want to see how the initial input image, how every single pixel contributes to this most crucial feature map. And so that's where the gradient comes into play. We're going to say that's step one. We're going to compute the gradient of our class C with respect to that last feature map, K, given ij. So we want to find how this linearly contributes to that feature map, how every single pixel. And so, and it's not just one gradient, it's going to be all of those gradients. So we're going to, that's step two, we're going to average all of those gradients together. Average gradients. Average the gradient score. And so we'll say, here's how that's represented. Here's the average gradient score of the class C for the kth feature map is 1 over uv, where u is the length and v is the width of our initial input image. We'll have two sigmas here to notify that we are summing all of those values, u and v, and dy, c, da, k, ij. And so that's going to average, and that's going to sum all that up, okay? And so that's that. Now let's get to the last step, step 3. And the last step, step 3, is to compute the class activation map. Compute GradCAM, using that summation that we just did. And so we can say that that entire last equation that we wrote can be summarized as the sum of all of those gradients with respect to the last feature map, K, for that given class. And so this is essentially a weight value. So all of what we just did was to create this weight value. And we multiply that weight value by the entire feature map. And so we computed every single pixel with respect to the final feature map. And that shows how each of those initial pixels in that image contributed to our specific class. So it partitioned or segmented the parts of the network that we care about into just the parts that contributed to our class prediction, and we multiply that by the full feature map, K. And my notes are so scribbly, but that's what we do. And so you would think, okay, that's it. That's going to give us our class activation mapping. So let's say CAM. But we do one more thing. We apply ReLU to all of this. ReLU stands for Rectified Linear Unit, and it's a type of activation. And in this case, what it does is, correct me if I'm wrong, it turns all those negative values to 0, so there are no negative values. And the reason we want to apply that is because we only want positive values, the ones that contribute to the final classification. And that's our last step. Step 3 is GradCAM. So that was kind of a high-level overview, but what better way to understand this than looking at the code? So let's look at the code. Okay, so now that we've talked about the math, let's write out this code demo. All right, so we're going to import Keras to make machine learning simple. It's a simple wrapper over Tensorflow, which is our deep learning library to build neural networks. Keras has this amazing visualization library called Viz that we'll import as well, which is going to help us visualize the class activation mappings. And then, of course, Matplotlib, which is going to help us visualize the image inside of this notebook. and then NumPy for standard data cleaning and matrix math. Okay, those are our 5 imports that we're going to use here. Okay, no, I'm not going to upright. Okay, so once we've done that, we're going to say, okay, so what is the network that we want to use? We can train our own network, but in this case, let's just say, let's import a pre-trained network, because what we want to do is not just build a network. We want to visualize its predictions, right? There's plenty of videos on building a network, but on explainability, not so many. So we'll say VGG16 is the name of this network. VGG16 is a 16-layer convolutional neural network, and we'll want to pre-process the input. And so Keras has that built in. So we'll say, here's our machine learning model. It's going to be a VGG16 model. The weights of this model are going to be literally from the ImageNet, are called ImageNet, which are the ImageNet weights. And then we will say, okay, so that's that. Import VGG16, yep, okay, great. And it's downloading that convolutional network, great. And once that's over, we can do this together, by the way, if you're not following. You can do this in your browser. You don't need to install anything locally, which is amazing. So now that we've done that, we can download those class labels. So this is our set of labels for everything that it's going to predict. And now we can say, so now what is let's see how many classes we've got. So let's say from that JSON file, which is that ImageNet, we just downloaded that. We'll say, what's the index and what's the label? And we'll have this empty list for that. We're going to fill it in a second. Now we're going to go through every single class, and we're going to add its label to our list that we created. Turn it into a string. And say, here's the number of classes. Dot format, length, class label. All right. We've got 1,000 classes. Okay, totally doable. Now we'll say, okay, let's visualize that image. Let's see what we've got here. Well, what we're working with here. We want to know what we're working with here. So we'll import the load image library to load it up and to convert it into array for further pre-processing in a second. And we'll say, here's the image, load the image using that load image function. It's called dog and cat .jpeg, which we don't have here. We're going to have to upload that in a second. Target size equal 224, plt.image show, image, and now we're going to show that image. So now let's upload that dog and cat image. So what we'll do is we'll click on upload, and then we'll click on dog and cat.jpg. And it's going to upload that image, and it's uploading. And now that it's uploaded, we can visualize it. Now we'll convert that image to an array to do some further pre-processing on it. We'll say that the image is going to equal pre-process that image. We want to pre-process that image. We want to get the prediction. And because what we're going to do is we're going to print out the prediction. So we'll say model.predict that image. Here are our top 5 classes, top 5 predicted classes right here. Okay, so Bloodhound, okay, it's saying mostly dog. It's going for the dog one. So now we want to know why. Why did it pick a dog? Why not just pick something else? So now comes the GradCAM method. So this is actually built into Keras under viz utils. So we'll import utils. And we'll say, remember, we take the last layer, layer IDX, and utils will help us find that layer with the find layer method from the model. And we're going to call it predictions. And we want to swap that layer with a linear layer. So basically, there's a softmax function at the end that's used to convert the the extracted features into a class probability value. And what we want to do is we want to convert that softmax function into a linear function because we are no longer classifying an image. We are using that and we're repurposing it for creating a heat map that we can overlay over the image and that can act as an explainable image for us. So we'll say swap softmax with the linear and apply that modifications to the model. Once we've done that, we will, in a single paragraph of code, we can see what's happening here. We say, so visualize cam is the method. So we'll say here is our penultimate layer, our last layer, and here is the class in question. So we want to know why it predicted this class in particular. And here's our seed input, which is that initial input image. And so here, using this single function, the visualize cam function built into Keras, we'll say given the model, given the last layer, and given this class, and given this input, and the actual last layer, not just the probability value, not just these linear layer that we just inserted, what is that class activation mapping, which is basically going to be this matrix of values, which is essentially a heat map. And it'll do that for us. All of that fancy gradient math that we talked about, it does that in a single line. And it says, hey, you got an error because you need SciPy. So I guess I missed a single dependency, SciPy, for scientific computing in Python. TM, scientific computing in Python. Okay. Got it. And now restart. All right, fine. And then once we plot it using matplotlib, we see that gradient class activation mapping overlaid over the original image, and it goes according to our prediction. It said Bloodhound was the most likely prediction, and that is what our class activation mapping shows. So that's that. If you want to learn more, I've got learning links for you in the video description. I've got the code for you in the video description. Shout out to fairyonice for the code. And thank you so much for watching. If you like this video, hit the subscribe button, hit the like button, and I'll see you next week.